Thank you. Thank you very much. And thanks for the invitation, everyone. I'm going to take a bit of a future approach to my talk this morning. I know you're learning a lot of hands-on about Fugaku and homogeneous processing. I'm going to focus on heterogeneous computing and try to shed some light on why we're seeing a lot more heterogeneous computing, and then some of the challenges with that are programming models, understanding how to program them. They're very complex pieces of equipment, and if you don't use them properly, you lose all the advantages of it. But first, this is a pretty green picture of Oak Ridge in the summertime. Yesterday, we got a massive snowstorm in Oak Ridge, and so we've got piles of snow, and the airport shut down, and all of that stuff. But the good news is, dog found a way to have fun in the snow there. He's in the backyard running around, having a lot of fun, and so hopefully we'll get home when we head back. But who knows? So let me tell you about my talk. If you look at the news, and I assume many of you, watch this on social feeds and other things as well, there's a huge demand for computing now. When I was in school, I had no idea computing would become so important to the world. If you look at all the social networking, if you look at Bitcoin, if you look at all the data processing, now of course AI, it seems like computing's insatiable. Not to mention our cell phones and all of that has been enabled by computing. The challenge is there's not enough power, right? And this includes things like building new nuclear power plants, which we're doing at Oak Ridge. Other consequences, like the power grid doesn't have enough capacity to support all of these data centers. Well, I'll say that's really a result of computing, the end of Dennard scaling and Moore's law, right? And what we're seeing is this massive uptrend in the amount of power we need just for computing in general. We've been thinking about this for a long time. The Blue Gene paper that was mentioned earlier originally had a goal of energy efficiency, and that's over 20 years ago. In 2010, there was a report that looked at building an exaflop system in 20 megawatts. And the conventional wisdom then was it was going to be a gigawatt to build a exaflop system. But we managed to build Frontier and then several other systems that have stayed within that 20 megawatt envelope. Now, of course, we've seen the specialization with GPUs. NVIDIA's the most valuable company in the world, right? I mean, who would have thought a company that built gaming GPUs is now the most valuable company in the world? That is still sometimes hard to believe, right? Anyway, we really have to start focusing on energy efficiency now. And in the short term, what we're seeing is CMOS specialization and integration. And so this is things like GPUs. But in the longer term, I'll argue that we are going to be looking at things like photonic computing and analog computing and quantum computing. And as a computer scientist at heart, I find that really exciting. The rest of the world thinks it's trouble, right? Because they have to have applications running on those platforms. They have to have people to program the platforms. They have to make use of them over decades. And so the software challenges is where I'm going to spend most of my time. And I'm going to try and just give you a taste of it. We don't have a GPU cluster set up for you today. So I'm just going to talk about some of the challenges there. One takeaway message is how convenient we have AI coming about at this time. 5 years ago, we just saw this rapid explosion of computing architectures, and we have to hire teams to port applications to each new architecture that came out. And now we may be able to ask ChatGPT to port my kernel for me. And so we're looking at a lot of tools to try and make that easier. So that's an overview. Let's dive in. And feel free to ask questions. I love questions along the way. If I don't get any, I might ask you a question or two to get your opinion on things. So let's back up. So power, is it real? Are people really building data centers? So the densest population of data centers in the world, as far as I know, is right outside of Washington, D.C., near Dulles International Airport, you see right there. And if you look at this diagram that the Washington Post published, it shows all the data centers that they have. And these are conveniently located in an alley where there's a lot of power, there's a lot of expertise, there's lots of resources there. This is a satellite photo in 2014 of the data centers in the area near the airport. And then in 2024, just 10 years later, you can see all the additional data centers. Family that lived next to the airport, I went up there, it's amazing. I mean, buildings as big as this one, 10 times as large as this, right, that are being built so they can put computers in them, right? And then, of course, in places like Tennessee, XAI is building huge warehouses. And a lot of the things you see outside, right here in this picture, is those are all diesel generators or natural gas generators, right? They're out there just generating power for all of these computers they have inside. And recently, XAI just published that they're up to 1.6 gigawatts of power in that area. And you've heard all the other announcements. I don't want to belabor them. But notionally, 1 gigawatt of power is about enough power for the whole city of Denver, Colorado, in the United States. And so that's, you know, that's got a lot of people worried. One thing this has really spawned is a resurgence in interest in nuclear energy. And so at Oak Ridge, since we have a lot of nuclear engineers and other things in the area, we've really been doubling down on it. This is an artist's conception of a small modular reactor that's being built now, and it's the outside of the actual lab itself, but it's off to a side where we used to have K-25 manufacturing plant. It'll be about 300 megawatts when it's finished. And this is actually a picture of the construction going on now. So, and they're planning multiple SMRs on that site. So it's real. People are spending hundreds of billions of dollars to build buildings, to buy GPUs, to build nuclear reactors. And again, if I would have asked you 5 years ago, where is nuclear? Most people would say build a windmill, right? Now it's just not happening rapidly enough, and so we see this nuclear transition. There's a lot of regulatory hurdles too that are being addressed in this process. So bring it back to DOE, HPC, and computing. This is the trend we've been witnessing over about the past 15 years. My chart only goes back to about 2012, but right on the cusp of that, we were looking at Oak Ridge, we had a system called Jaguar that was a sea of AMD processors, x86 processors. Argonne had the Blue Gene Q systems, Livermore as well. Those were the world-class supercomputers at the time. And then as we started to transition over the years, you know, we couldn't find a way to keep up with the performance that we needed without becoming heterogeneous. And of course, you all know about gaming and graphics and all of that. So at Oak Ridge, Titan was our first system, DOE system that had NVIDIA GPUs in it. And so that's hard to believe. That's, you know, 13 years ago now. And so after that, we had the Intel Knights Landing. Then we had another system, the Summon NVIDIA system, and then we bought Frontier. A new system has just been announced, Discovery, and it's going to be another GPU-based system with AMD. Plus, there's a bunch of NVIDIA systems being announced. So it's pretty clear that this move to heterogeneity is, you know, it's not just a one-of thing. It is a major trend in industry. So, and again, if you think back just a little bit more, that's great. I mean, industry's adapting, DOE is adapting, our users are adapting. CMOS is working the way we expect. It's letting us build these GPUs out of techniques that we know how to use. But then we get to this power part, and that, again, is the part where, you know, for about a few more years, we're going to continue on this trend, but, you know, there's a limit to how many nuclear power plants you can build and how quickly you can build them, right? And so people are going to be looking for additional ways to actually do AI without more power, and that would be energy efficiency. Point here is the NVIDIA's Blackwell 200. You know, it's got a high end of 2,700 watts, and that's for the node, not just the chip. 2,700 watts is a lot, right? There used to be a time when the whole computer you had wasn't even close to that. And now we're talking about just that complex that has the GPU, a CPU, and some memory on it is 2,700 watts. So it doesn't take long until you're out of power. TSMC is telling us this is their plan. This is from about a year and a half ago at the ISSCC conference in San Francisco. And this is what we refer to as heterogeneous processing, but it's brought it down to the chip design level. And so there's a technique called heterogeneous integration. And what that means is most of our processors in the past, like the GPUs, have been all the same processing technology, like CMOS at 3 nanometers. But what heterogeneous integration allows you to do is you can pick specialized pieces of different types of chips and then put them on a package together and integrate them. So you can basically build whatever you need, a domain-specific processor, right? And that's what people are doing, and in fact, that's what TSMC is saying will take us to 1 trillion transistors on a package, right? And so that seems believable. That seems like the way we're going. The key here is people can compose those packages any way they want. If you, I'm certain all of you have at least one cell phone on you, right? These are heterogeneous processors. They have audio processors and video processors and CPUs, multiple CPUs and GPUs in them, and that's just the way you do this, and it's largely because of the energy efficiency that you do that. And of course, we're seeing it, you know, across the industry. We've got the GPUs, we've got TPUs at Google, Snapdragon I've already mentioned. Heterogeneous computing is here. So I'll stop for a moment and ask, does anybody have any questions about any of those points? Nuclear power or cooling or data centers or any of that? Yes? I don't know if there's another mic. I can bring it. Okay. Here, I'll let you use this. It's on.
Okay. Thank you for giving us a different perspective. Thank you. My question is, you mentioned about the electricity and specifically, but what about other resources? We see we have used a lot of cooling liquids, other things to really cool down the systems. And the aftermaths of using these technologies to the industries, cities, and we are also trying to go to the green energies and also trying to follow the SDG, the goals.
Right.
Yeah. So what's about that? What's your opinion?
Yeah, that's a great question. You know, you naturally think of things like water and for cooling or for other purposes inside a data center. There's the supply chain issues with different types of rare earth elements and things like that that play into this. There's a lot of effort underway now to understand like the critical minerals. At Oak Ridge, we have a project that's looking at how to substitute other minerals and rare earths for things that are in short supply. Water is actually interesting because it's not used as much as you think. And what I mean by that is that they're moving toward a high temperature cooling And a lot of those use coolants that are in a closed loop system. So you're not pulling water like out of a river and then cooling the system and then dumping hot water back in the river. It's all in the same loop, and then that gets exchanged with air, or it could just heat up some water and dump it back in the ground. So it's not, it's not really consuming it or evaporating it in some sense.
Is it really good for the environment, is that what say?
You know, I don't know. The thermal thing has been around for a long time. I mean, we've had steam engines and all of that, so there's been, I don't know how bad that is. The rare earths and some of the other materials that you have to use to make some of these things are, pretty nasty, right? But at least in the U.S., they're, those things are pretty highly regulated. The other thing is the carbon and carbon sequestration. The good news is nuclear power is mostly carbon free, right? That's the one that tricks everybody out because you don't think as green as being nuclear, but it's one of the more green power sources we have.
Thank you.
Okay, yeah, great questions. Oh, yes, we have one back there.
Yes, thank you. Thank you very much, Jeff. So I would like to ask about, the another method of cooling system, which is immersion. I know that the industry is exploring immersion as one of the option to cool the system down. So how do you foresee it? Will it be the next like the next generation of promising cooling?
Yeah.
And what's the pros and cons?
Sure. Yeah, those are all, mechanical engineering problems in some sense. I have been witness to this. One of the very first supercomputers I saw when I had an internship was I was in a national lab and I saw a Cray C90. And I think this was around the mid-90s. And you walk in and it's in a pool of fluorine, which is coolant. That everything was submerged in the fluorine, and they were using liquid to cooling. So that part's not new in some sense. People have been looking at cooling, and they use it for other things too, like various industrial processes. There's a lot of technology out there. In the past, national labs have tried to stay away from that because it typically increases your maintenance costs. So when you have to debug a memory cell or pull a board out, there's a very complicated process you have to go through to decouple all the plumbing and make sure you don't spill any of the liquids or things like that. But that said, everybody's moving to that now because there's no other way to evacuate that amount of heat out of a system without using the liquid cooling. And if you've been to supercomputing, have any of you been to supercomputing conference? Okay, there's a few hands. Good. You need to go supercomputing. In the past 2 years, we've actually had oil companies at supercomputing because they're trying to sell this cooling technology to the people building these systems. And so it's an area of active exploration. Thank you. So let's keep moving. Heterogeneous computing, what am I talking about specifically? So if I gave you an abstract diagram of what heterogeneous computing looks like, this is what we think about today. You've got a host with a CPU. Many of you, I'm sure, have programmed CPUs. They're really optimized for serial logic and minimize that latency through the control stream. They run databases and cloud servers and operating systems and all that kind of stuff. They manage the memory and the I/O for the most part transparently, and then they have really high clock speeds, and they manage this complex control logic by using branch prediction and caching and those types of things. The GPU takes a different approach. It really has simple processors in it, and they don't do all of that fancy branch prediction and all of those other things, and it doesn't have as many instructions that you would normally see in those CPU cores. And so the trade-off is, in the same area, you can have a lot more of these. And when I say a lot more, I'm not talking about 10 or 20 or 100. I'm talking about thousands, right? you might have, 64 cores on a contemporary CPU. You might have 4,000 cores on a contemporary GPU. And so the benefit there is if you have a lot of data that's truly parallel, that you can truly process in parallel, it's fantastic because you fill all those cores up and let them compute, and then they reach out to memory, they pull in the data as they need it, and then they just, win because you just keep them busy, right? There's this huge throughput. That's what you see often referred to as latency versus throughput. And so this is considered a throughput architecture. And of course, there's ways you need to think about programming the system that's different. Over there, you see the caches tend to be very huge in the CPU architecture. And again, it's to minimize that latency so the data is as close to the ALUs as possible. And then the GPU architecture has some cache and some control logic, but it's a lot less. And the benefit of that is you can have a lot more of these ALUs and cores and just do more parallel processing. When you look at the system, it's really this hierarchy of scale. And so, and once you start programming CUDA, which I would encourage you to do, there's a lot of tools out there that are free you can download today. You have simulators. If you don't have an NVIDIA card, you can use those, and some of your laptops have NVIDIA GPUs in them. But highest level, you have that data segment, and in NVIDIA terminology, you would think about it as a grid, and that's just a name they came up with it. It's really a collection of all the threads you want to run in a kernel. And then each one of those threads decomposes again down into called a thread block. And then each one of those threads, like we were talking earlier, really looks like a serial thread that you look at for a CPU, right? And so what you're doing is writing this thread, and then the system more or less maps it onto the system, maps the data onto the system. And you can see there, it's got queues and all of that logic that really do that scheduling for you. But basically, you're mapping those grids, thread blocks, and threads onto these SMs that I showed you earlier. And the SMs are those blocks that you see there. The idea is it's not magic, right? The challenge is that you really have to be careful about the way you program all of those cores, because effectively what you don't want to do is turn it into a serial program. I think parallelism, the less interaction they have, the less synchronization they have, the faster they can go. But if you even accidentally, unintentionally introduce things in that cause synchronization and communication between the cores, then it slows everything down. And you can be in a situation where it's operating a lot slower than the serial core. But then here, if you just look at this example here, and again, we don't have time to dive down into it too much, but here, this is a visualization of a properly synchronized add instruction that's happening on all these different threads. And the nice thing about that is that all the data is available here, they compute, and then when they're finished, they're all writing their data out. That makes it easy for the memory controller and other things to make sure that the data is, that the memory controller isn't doing a lot of extra work. Here, what happens is when you start introducing things like if statements, conditionals in your code, then all of a sudden you start introducing these inactive sections. So if you're computing for a while and you hit an if, well, everybody who doesn't follow that block is going to stall, and you want to minimize that. And so what this is just illustrating is that if you have a lot of control or a lot of randomness in your control, you're going to end up with less efficient throughput computing. But that's just a really high level way to think about it. They call this divergence in GPU land. When the threads diverge, that means the control diverges. Then you you really start serializing the hardware execution, and that cuts your throughput. You still have a memory hierarchy, and again, this is something in a GPU that is different, but it's similar at a high enough level. You look at global memory, it's the normal memory that you think of. It's very large, it's very high performance. It does have relatively high latency, and that's on the order of maybe hundreds of nanoseconds or maybe even more. Then you have this L2 cache that all of the SMs in your GPU can see, and it's relatively fast, and you don't really manage that. That's more or less hidden from you. Then as you get a little bit closer to the actual compute, you still have an L1 cache in each one of those threads, but you also have some shared memory. And this shared memory is nice because you can manage it very carefully. And when I say manage it very carefully, you have to think about how many data structures will fit, right? And in some cases, it's up to you to make sure you know how big your data structures are and that they fit there. It can be a bit tedious at times, but there are tools and other things to help with that. And then finally at the top, registers, and if everything fits in registers, you hit a home run, right? That's the way to think about it. There are other things here that aren't really illustrated, including like atomic operations and some of the communication primitives, but those are things that you can learn about as you make your way through this. So if you look at just a quick kernel here, the way you write, when you write a serial piece of code, you really can follow the logic the whole way through. And you have an array, and you know what element you're indexing. And what happens in a CUDA program, since you have thousands of these, you're not programming each one individually. Basically, you have to come up with a pattern that the GPU can see, and then take that pattern and map it on all those SMs. And what the scheduler does is really give you information to do that. So if you look at just a vector add kernel in CUDA, it gives you this global index. And that global index is not something you really know when you write the kernel, but they tell you how to calculate it. And that is, they give you these structures: thread index, block dimension. And you take those and you reference them in the beginning of your computation, and then you index your data structures using that thread index, right? And that's the way you think about it. This general pattern can be given to any of those SMs that I showed you earlier, and it tells it what those parameters are, and then it's off to the races. It goes out and fetches the data structures for A, B, and then writes it to C. And then it tries to synchronize them, right? And so this is where, if you have thread divergence and you start adding ifs and other things in there, then you lose performance. But in general, as you can imagine, it performs really well. That's why they're doing well. If you look at that global data structure at the top, it really is a linear ordered array of data, and then it decomposes as you see here. So if you want to know the specifics about how you calculate the offset and the local ID, that's how it's getting indexed in there from each one of the kernels that get launched. And then at the highest level, this also kills performance if you're not careful. So you still have the CPU, GPU set up. The CPU's executing. You as the programmer have to think about what you want to use the GPU for. And there's some trade-offs here. One of them is that you want to select the right computation for the actual GPU. They do really well at matrix operations and BLAS operations, linear algebra, and a host of other things. And NVIDIA and other vendors have a lot of information online about what works well there, but it has to be enough work, right? If you're going to take microseconds to transfer the data from the host memory over to the device memory, have it compute, we're talking microseconds, maybe more, tens, hundreds of microseconds to get it up and running, launch it, execute it, get your device back. And so sometimes it's just easier to keep your operation on the host and just compute it there because that's an expensive operation. And so what you see most people doing is really picking a handful of kernels from their original computation and offloading those, but not everything. It's not like you start the host and then you just run everything on the GPU. You pick a few of your important kernels, and when I say important, I mean amount of time you spend there, amount of compute, flops you compute, and that gets sent over to the GPU, and it might run for milliseconds or maybe even seconds, and then send the data back. And so that's a way to make efficient use of that. So we'll stop there. I'm going to jump into a little bit more detail about programming challenges here. Has anybody done any CUDA programming already? Okay, all right, we've got 5 or 6 people. It's very it's very popular, and it came out of the gaming community. Someone said, hey, I got a bright idea. These parallel operations we're using in video games look like they could be useful doing other computational science. And so in the 2005 timeframe, this little renegade fraction went off and started programming GPUs to do other cool stuff. And they blossom because now GPUs are AI. Right? They're being used for AI a lot more than they are graphics and video games. And so it's amazing how that pans out. Any more questions on that? Okay. So the good news is that, if CUDA doesn't appeal to you, there are a lot of ways to program heterogeneous systems. And it's not just figuring out what your thread indices are and things like that. There are various standards, and I've just listed a few of them here to get you to know about them. AMD GPUs have a programming system that looks very similar to CUDA. It's called HIP, and it's very direct on the hardware. You get to see a lot of the benefits, the pros and the cons of the hardware when you use CUDA and HIP. You get to manage a lot, and so it's your your fault if it doesn't work well, and your benefit if it does work well. A lot of applications people want to use higher level standards, and we've spent a lot of time and a lot of money trying to make sure there are standards out there so that you can write your program once and run it on any heterogeneous architecture. And that's difficult, but it's getting there, right? Look at OpenMP offload. There's a standard called SYCL that's C++ basically. You don't have to get down to the level of CUDA or HIP. And you really have a single source C++ program. Basically, you write it once and you just recompile it for each GPU that comes along. And then we have an experimental framework called Iris, and Iris is this intelligent runtime, and what it does is it allows you to run on multiple GPUs at the same time. You can have FPGAs, you can have, even today we have a quantum computer support in Iris, so you can have all of those in the same application. And it's still a prototype, but it's very good for the research that we're doing because it helps us identify where some of the challenges are. So in that vein, about 5 years ago, we created a benchmark suite. And if for any reason, just to give you a flavor of what the coding looks like for all of these different programming models, I'd encourage you to go download it. It's on GitHub. There's about 500 benchmarks that we've written in different programming models, and they all do the same. Each one of the benchmarks does the same thing. You can do simple core math like Saxby or DGEM, but we have them written in CUDA, HIP, SYCL, OpenMP, and we're adding a few other things there. And so if you're just curious about what the head-to-head source code looks like for those, I'd encourage you to go there and download it. And it has, you know, CMake files and things like that, so you can basically launch it on your system and run all of them if you want to. We use that for tracking the progress in programming models and other things. And then if you just look at what you can see there, this is Saxby, 3 ways, and it just kind of shows you what the different abstractions look like. So CUDA, everybody calls this the metal because you're close to the metal, right? It has the block index calculation and everything that I mentioned earlier there. And then if you look at OpenMP, if you don't know about it, is it's really a annotation that you put in a serial program. And that annotation tells the compiler to take a specific piece of code and make it parallel or offload it. And so that's what's happening here. If you take that same Saxby, if you get rid of this gray pragma here, you just have a normal for loop, right? This is something you've probably written many times this week already. But if you add the pragma OpenMP parallel 4, it takes that and makes it parallel. And if you configure the compiler the right way, it will offload it to a GPU. And then on the right is our Iris system. And it basically uses a task dispatch, and it can take either one of those kernels and launch it on a GPU or a CPU or even an FPGA, and it will pick which one of those source codes that it needs for this specific architecture that it's working on. So I got about 5 minutes left, so I'm going to speed a little bit through here. I want to highlight a few other things. This is Iris, and this is, you know, the reason we started this project about 5 years ago is because we think this is the way it's headed. We think in the next 5 years, we're going to have people writing programs that have quantum, that have GPUs, that have CPUs, that have other types of specialized processors like AI inference engines in them, and you've got to write a program for that, right? And so Iris is meant to be a tool to identify the challenges for that. And it's available. I'll share the slides with you. It's on site, online, and you can download it from GitHub as well. But let's jump ahead. So I mentioned, you know, kind of one of the clever things that's happening now is, you know, this AI revolution, if you will, is really impacting a lot of areas. And one of those areas is writing software. I don't know, have any of you used Claude Code or Codex online? I have. It's pretty amazing. I mean, I have the HeckBench benchmark suite, and you know, I converted it to use CMake because it was a collection of many different benchmarks and build systems and all of that. And so as an experiment, I was like, let me see if I can take Claude Code and create a CMake build system for this. And I did it in 2 days, right? And I'm a manager, right? I'm a slow coder these days. I'm not as good as I used to be, but I could create a build system for 500 benchmarks in about 2 days using Claude Code. And so I'd encourage you to take a look at it if you haven't. And this is something we worry about in the DOE. We've got this post-exascale era where we've got all these different architectures showing up. And worse, they all have their own programming model. Not everybody likes to play nice, and so they go out and create a new programming model for their accelerator, and then we have to adapt to it. But then also we've got, you know, people not knowing Fortran. And so, you know, we're doing things like doing a lot more work with Python and Rust and Julia and those programming languages. And so, but a lot of our codes are in Fortran, so that makes it a challenge. So one of our ideas was started about 3 years ago, and that was to look at how we use LLMs to really facilitate this. And that means we take like a legacy Fortran code and use what we call ChatHPC to convert it to a maybe C++ or Julia or something else. And so that's what we've been working on. And there's a lot of details here. We had a paper at SC25 just recently that goes into more detail. And this is, again, downloadable on GitHub. So you can take a look at it if you want. Basically, we have a base foundation model that you can get from Hugging Face. We fine-tuned it, and we fine-tuned it for the different programming models that we use, and that includes things like Cocos, MPI, OpenMP offload. And then what we did was give it to the user so they could go through and just put queries, prompts in. Here's a piece of code. Make this code, this CUDA code hip. And then it would generate the code. And we found that by using the fine-tuning, we could really increase the accuracy. And what I mean by that was we went out and really looked at ChatGPT and some other tools. And again, you know how fast-changing the AI community is. So some of these numbers are older and they're improving. But the idea was by using the fine-tuning, we were able to really improve the ability of LLMs to give you correct code. And we had verification steps and all of that in there. And so there's a lot of promise here. And so if you haven't looked at it, I encourage you to do so. Chat Cocos, that's just another example. We were able to improve that. And so if you haven't started using chatbots yet, I would encourage you to do so. It's really a game changer, and I'm pretty skeptical about these things, but it's very very positive. So in just a minute I have left, I'm going to just say a word about next generation technologies because that's where I spend most of my time. And so we've got active projects going on in all of these areas. Neuromorphic, analog, quantum, and then standard CMOS just gives you kind of the state of the art. We've got a quantum science center at Oak Ridge. Quantum is making a lot of progress. There's a lot of money being spent on quantum. It will probably be used as an accelerator for things like quantum chemistry or specific optimization algorithms. It's not a general purpose system, but as you know here, there's a quantum system downstairs, right? So it's not just an imagination. Neuromorphic, everybody for 50 years has been trying to emulate the capability of the brain that's about 80 billion synapses, neurons and more synapses and at 20 watts. And so we're not quite there yet, but there are some very targeted uses for neuromorphic computing like sensors, using them in sensors to detect features that is very good. And then analog. Analog is the original computing, right? So one day I was challenging myself to find the earliest publication about analog computing. How old do you think analog computing is? Does anybody want to take a guess? I found a real paper. 1888, right? And it was is the Royal Society of London, I believe. And so it's very, it's been around for a long time. Of course, it has its problems because it's susceptible to thermal and noise and all of that stuff. But with that, I would wrap up. Just to recap what I talked about here. I know you're not spending a lot of time on heterogeneous computing today, but I'd encourage you to look at it. We've heard about this unprecedented demand for computing. You guys are doing computing, so the future is bright. We got to think about efficiency, right? We've got to have more efficient software, more efficient hardware, more efficient algorithms, all of those things. And then I just highlighted a few things we're doing today with the software and the challenges of taking some of those legacy applications and workflows and moving them to heterogeneous architectures, and we hope AI and LLMs will help. So with that, I will stop and answer any more questions you all have. Thank you very much for your attention.